there we go. Okay, thanks. Okay, so there's the title of my paper, which I didn't get to Olympia in time to make it onto the programme. Why I don't think solving the measurement problem is the key to understanding molecular structure. I should say that I really like Alex and Vanessa's paper. It's an interesting argument. I really don't like the conclusion, so it's up to me to explain just for myself, you know, where in the argument I get off, where I stop agreeing, where I to mean. So what I'm going to do is going to be a little bit in the first half of the talk is going to be a little bit negative and like sort of saying, well, where would I get off? Where would I be skeptical? And actually, it's got quite a lot in common with what Olympia's just been saying. And it's really, I think the essence is it's how we interpret the mathematical relationship. Supposing we could see the ground state of the Coulombic Hamiltonian as a superposition, what would follow from that? Well, actually not very much, because I think it takes a little bit more for something to become an interesting case of the measurement problem. I also think the case is the same thing is the case about symmetry. I think we can learn things about relating some of the problems about deriving molecular structure, in particular cases, from the measurement problem and from symmetry breaking, but I just don't think that you can regard them as special cases because and I also don't think that solving the measurement problem would give you a solution. In many cases, it gives you basically what I think is quite a sophomoric answer to the questions, which then, so if it doesn't really solve the problems that I think Olympia and I are obsessed about, then they aren't the same problems. Okay, so now what do I do now? I go like that, yes. I've been thinking about this a lot, and just yesterday I just jotted down, I've been writing another paper on this. So here's what, I think I could be wrong, but here's what it takes to relate some interesting foundational problem to the measurement problem. So you've got to give a more or less rigorous analysis of the relevant kinds of physical state, including an account of how they can be prepared, because you want these states to be kind of worldly states. They're kind of there. We can see them. They're around the place. We can see examples of this in more or less rigorous terms in this, just quantum mechanical descriptions of the Stern-Gerlach apparatus. We can prepare states. We can ensembles of silver atoms which are in superpositions of one state or another, and we can display that behavior. Ditto, in much less rigorous terms, Schrodinger's cat. Then we can also give more or less rigorous account of how to perform measurements concerning the relevant kinds of physical state. Thirdly, we can show how the states are prepared in accordance with one, or in something like a superposition of states corresponding to two. Maybe this is all sort of naive movie, but this is how we apply the measurement problem we give ourselves then finally, we show how various interpretations of quantum mechanics shed light on the foundational problem of interest given 1 to 3. So they give us a kind of a story about what's going on when we look at trends going between various states as described in 1 to 3, and we show how we see how interesting they are. Okay, so where do Alex and Vanessa's how far does it kind of meet these requirements? Maybe these are really too strict. Maybe I'm being really pedantic here, but well, we don't really have an analysis of structure in quantum mechanical terms. I don't blame them for that. That's they kind of follow Claverie and Dinier in citing a kind of structure found that we find in internuclear correlation functions, but that's not the same as a classical molecular structure. We don't really know what a measurement of structure is. Locating nuclei might sample into nuclear correlation function, but that's not obviously relevant to a classical molecular structure that's consistent with a number of different things. Well, we don't really know that quantum mechanical systems are a superposition of classical molecular structures. There's the argument. I think there's a I'm not sure about the one. I mean, there's a general mathematical sense in which you can understand as being represented that way, because you can give an argument based on symmetry properties, which is something that, well, various people, Claverie and Dine do that, and Alex and Vanessa, but I'm not really sure how to interpret those arguments, because it's an argument about, representing one kind of state in a basis of states of another kind, and I'm not really sure what follows from that. What we really need to know is about, well, being in superposition of a bunch of states is not sufficient for generating the measurement problem. We need to know something about the physical significance of the system, which is why I was talking about, preparing the states, doing the measurements, and so on. Once again, this is all being, super pedantic. Now, Primas and Woolley, as we all keep saying, related the puzzles about structure to the interpretation of quantum way back in the 1970s and 80s. And it's been clear since then that many interpretations could in fact solve some of the problems, but in really quite unimpressive ways. And this is why I kind of don't think that solving the measurement problem, if it's solving a measurement problem is picking one of the interpretations, I don't even know what counts, but it seems that it's hard to see how picking an interpretation often gives you very much of an answer to the kinds of questions in some cases that we can give. So if solving the measurement problem is picking an interpretation, and the interpretation gives you a highly unimpressive answer to the problems that we're going on about, then I don't think they're the same problem. So Alex and Vanessa do draw from their analysis the conclusion that strong emergence is undermined. I have to say, now I've got to get this point in. In my view, their argument begs the question by citing only interpretations of quantum mechanics that are consistent with Magdalen's completeness lemma, and which are therefore the strong emergentist is going to say that they beg the question against them. Moving on to symmetry breaking, I think I'm rattling through here. How am I doing for time, Eric? Good, right. Anderson's discussion of the ammonia molecule depends. What about the relationship between structure and symmetry breaking? Here again, I wouldn't deny. Obviously, there's interesting things to be said about looking at some of the problems about where structure comes from in these terms, but that doesn't tell us that all the cases are going to benefit from being looked at in these terms, especially if the structures could be arising in different ways. Which again is something I'm open to. Clearly, some symmetry breaking is interesting. It is interesting to look at some of these problems in that way. So we've talked about Hund's paradox, and there's Anderson's discussion of the ammonia molecule that Alex and Vanessa cite. But here there's a particular case, and here maybe I'm being really super pedantic, but when Anderson's discussion of the ammonia molecule and the symmetry properties of the problem and the symmetry properties of the ammonia molecule itself, and how we commensurate those two things, well, Anderson, as it were, gives himself the assumption that the two asymmetric states correspond to minima on a single potential energy surface. There's a mechanism by which a single molecule can traverse this energy landscape in kind of pretty short order, and that's why we can say over time, well, actually very short time in the ammonia molecule, we can say the overall symmetry is preserved. The timescale relativity of this. So the timescale relativity makes this less plausible in the case of optical isomers and enantiomers, because it just seems, once again, it seems, I don't know if people know the English word Pickwickian. It's just, oh yeah, well, I'm sure it'll turn into this other thing if we wait long enough. But if we wait long enough, longer than the lifetime of the universe, I think we're all dead. This is not an observable process. So I wonder. It's kind of a metaphysical explanation, but the main thing is that, as I understand it, what quantum mechanics, what tunneling involves is a bunch of states corresponding to minima on a single potential energy surface, and the molecules in those states get between those minima by tunneling through the energy barriers. Yeah, maybe it means something else, but I'm not convinced that, as it were, a transition between various isomers that share the molecular formula CHHH H8 could be modeled that way. Let's see, but is there a single energy landscape? Is there a process by which things can get between the in the minima? So once again, it's not the, it's the, as it were, the physical plausibility of the various mechanisms, our interpretation of the situation as a whole. So now I'm going to get on to the world according to Hendry. So my starting points are, firstly, realism about structure. It's one of the longest lived parts of science. 1860s, we have all these lovely hypotheses that gave us stories about the symmetry properties of molecules, and time has given us those. Molecules have got structures. The second thing I'm surprised by is that looking at the problem structure as a problem of as an instance of the quantum mechanical measurement problem, leaves out the, I think, crucial information that these are systems of electrons and nuclei interacting in certain ways. So we've left out anything that's internal to the system. We're just like waiting for the universe or the environment to give us the structure. So I'm not presupposing that these things have got to carry their structures around. I'm not trying to do anything like that, but I think we've got to take into account the well-defined physical conditions under which these things arise, and that we've got a guide to that, because we've got, when we're mathematically applying the approximations, the Born-Oppenheimer approximation collectively, that allows us to explain stable structures, well, these correspond to physical conditions. There's the approximate adiabatic separability of nuclear and electronic motions. There's the localization of the nuclei, and there's a third condition, restriction to a single classical structure. I think we leave out these conditions, we're missing what makes things behave like classical molecular structures. I should say that this is based on joint work with Robert Schoonmaker, but the gloss on it, obviously, Robert is a physicist. The gloss on it no doubt reflects my misunderstandings. So here's the idea. How am I doing for time, Eric? Because we've got a few minutes left. Thanks. I take it that was a 4 minutes. I'll rattle through. Adiabatic separability relies on introducing an effective field theory. So this is just the idea that the nuclei and the electrons, you can each regard one of them as providing a sort of a background field. This comes up in different ways. I mean, it's sometimes given in terms of the different speeds that they move at and the different masses of the electrons and the nuclei, but that will be a bit surprising because adiabatic separability doesn't apply to every system of electrons and nuclei. That mass ratio is a constant, so it can't be enough. Obviously, there's a substantive assumption about the way that the electrons and the nuclei are collectively interacting with each other. Making that assumption enables you to will give you a clue to introducing an effective field theory. Each one, as it were, sees the static field. That's the adiabatic separation, so you can keep the form. The justification of of an effective field theory of this kind is not that it's deduced from the exact quantum mechanics, but is shown to be dynamically consistent with it, i.e. to make similar predictions about how the system's going to evolve over time. So that would be claimed if we wanted to do the emergence talk, which would be part of the claim for non-reducibility. The other interesting thing about it is adiabatic separability licenses a novel representational device. This I completely take on trust. The potential energy surface in terms of which the stability of a structure can be explained, i.e. because it's a local minimum on a local potential, it's a minimum on local potential energy surface. Otherwise, the energy of the system isn't a simple function of nuclear configuration alone, which is the traditional potential energy surface. Secondly, there's nuclear localization as novelty. Brian Sutcliffe and Guy Woolley have been worried a lot about the neglect of a violation of nuclear particle permutation symmetries. I sent a version of this argument to them. They really hated this, so let's see. But anyway, it's demonstrable that if the nuclei are localized, for instance, by their interaction with an electron density distribution, then it doesn't make a difference, dynamically speaking, in how the system evolves, what kind of quantum statistics or indeed classical statistics one applies to them. They are localized for quite long, over quite long timescales. This suppresses the particle permutation symmetries. I mean, not forever, it's not magical, it's just you've got things which are relatively localized. And the symmetries, you know, thought about pedantically, they imply processes that express those symmetries, the equivalents of, you know, transformations you can make in the system. So the transformation in those particle permutation symmetries are nuclei, as it were, swapping. So once again, nuclear localization is not deduced from the exact quantum mechanics, but is merely shown to be dynamically consistent with it. So here, once again, drawing on my physicist friends, there's a nice example of failure, which is protonated methane, where the re-expression of the particle permutation symmetry is required to account for the molecule, the behavior of the molecule, the two closely lying protons. I can give a reference for that as well. And then finally, there's something we called, oh, you can't see the nice diagram there. I don't know what you can see, but the adiabatic separability and nuclear localization are necessary for bond structure, but not sufficient. We've always known that not all structures are neat, well-behaved classical structures. Cyclobutadiene, for instance, and these are my friends in the physics department who did a nice, you know, recalculation of the structure of cyclobutadiene, tunnels between two distinct structures, and you can detect different structures with different symmetry properties depending on whether you use X-ray, catch it in a lower symmetry structure or a higher one. Where you can think about it as sort of averaging over a tunneling between, so you get a square structure. So here's the thought: tunneling is the normal quantum mechanical behavior where you've got these systems on these close lying minima with respect to each other. Classical molecules are restricted to a single structure once again by their well, really by the structure of their local wave, their local potential energy surfaces. So the dynamical restriction to a single structure is a further necessary condition. So there's the thought. I just think we can't ignore, wondering where molecular structure comes from, we can't ignore what's going on in the molecule. We can't expect that difference to be entirely extrinsic. And given that there do seem to be necessary conditions for the emergence of this structure, they've got to be part of the explanation of why that structure exists. Now, that to me begs the term emergence, but you know, let's go on to there. That's not an issue, and certainly not strong emergence. That was only a fight that I got into because when we were first talking about the non-derivability, there are lots of ontological reductionists in the philosophy of science and in metaphysics who would always come back with these stories about the completeness of physics. So that's why I got into that particular fight. It's not particularly one that I wanted to take up. But anyway, I'll leave that dialectical point there. Anyway, thanks to Alex and Vanessa for a very nice challenge to make us say what we do, and to with Olympia for her paper. That was very stimulating.
Okay, thank you very much, Robin.
I should stop sharing now, shouldn't I?
Well, you can. Okay, any questions? Yes, I see Vanessa has a question.
it's not so much a question. Thank you, Robin, for your talk. I just wanted to thank you, both of you, for reading our paper so carefully and doing such wonderful work on it. It's really an honor, especially from people that have worked for so many years on this and that, you know, I've learned from. So it's really an honor. I think Alex agrees with that. Yes. I don't want to go into the technical stuff because I need to do some reading first and kind of think about it a little bit more carefully. But I have a general philosophical question about your understanding of reduction, because it seems that you assume a very strict understanding of reduction, in the sense that for you to accept reduction, you have to have strict deduction from first principles, which I don't see why this should be the case, at least metaphysically speaking. Why should we have such a strong requirement in order to maintain a form of reduction, I suppose?
Yeah, no, good. I mean, I didn't want to make today's thing all about reduction. I was just got sucked into that because you mentioned it in your paper. Yeah, no, I suppose I think about it this way. I mean, I just don't know why we use the metaphor at all, if a metaphor it is, and I mean, if it means something, it means being able to, as it were, abolish something as a separate posit, and that means I mean, I think that's a strong claim, and it needs quite a strong justification. So that's why. So I mean, you do often get people. So some people, there's a I'm just trying to remember what is. It's a book, and sorry?
Atema?
Yeah, thank you very much. Excellent, Eric.
Yes.
There aren't many books on these topics, are there? Yeah. So yeah, and he sort of talks about, oh well, we've got this non-deductive. I wonder. I mean, it's a really interesting book in lots of ways. Really detailed look at things. But I wonder whether, you know, he kind of calls himself a reductionist, and I sort of think, well, why are you a reductionist? Because a lot of the things that you would think of as picking out the reductionist position have kind of gone. So this ability to kind of do away with things, do without things, that requires. I think that's just dialectically. I think that's a strong claim that requires justification. So, and if we have to make the separate posits of things, even in practice, and I think that's the right way to think about how we get information about what things exist and what things have to be posited separately, as it were, when we're in the ontology room.
Okay. Thank you. And Olympia is waiting to ask a question.
Well, regarding this last comment, I wrote a comment about this book saying exactly what Robin said.
Yeah.
I mean, why not talking about intertheory connects relations and talking about reduction? If you make a lot of conditions, if you include a lot of conditions for the connections. But okay, I will make only thank you for your talk because it was very, very clear, and I will make 2 points to support your, I mean, emergentist or not reductionist point regarding the nuclear localization. No, first regarding symmetry breaking, when you draw the potential energy and the possibility of tunneling, the potential energy to draw this potential, you are already considering the nuclear structure, because you are clamping the nuclear to make this. I mean, you are putting the solution with by hand. So I mean, yeah. Novelty is because you have to put it to talk about potential energy and tunneling. So this is the novelty, I mean. And the second point regarding nuclear localization, it's a question. You are saying that you can break the symmetry, the parity symmetry between, in the case of a nuclei, because you are describing it in the electron density framework.
Yeah.
I think that I'm asking you, there are some views, perhaps if you can, or to discuss with Robert, there are some views that try to go beyond the Bohr-Oppenheimer approximation by treating electrons and nuclei at the same footing. So they treat electrons in the potential energy of nuclei, and nuclei in the potential energy of electrons. Anyway, in any case, so in this case, perhaps you can distinguish, you can put names to nuclei, but in any case, there is a very strong approximation there, like you said. I mean, the adiabatic separation and the fact that the total wave function can be expressed as a product. I mean, that there is not entanglement between the electrons on the one hand and nuclei on the other hand. I don't know if this is what you were meaning with in the case of nuclear localization.
Yeah, no, I think it was. I can meant like something really basic, that you don't what you've got. If you, we're often wondering, we've got these different identical particles, but the way that we individuate the structures seems to presuppose that we can individuate them. Well, maybe there's an explanation of that fact that you can have not localized bosons, of course, because bosons we can't, as it were, presuppose boson identity and then throw it away again, but we can, because we're not given it in the first place. You don't need to presuppose that. You can just have something. The reason why you can stick a label on it, you get to stick a label on it just for as long as it's localized. That's the point. So it's a quantum of boson density that you've got there, and that's what you stuck a label on. So nothing fundamental is being violated. It's just this idea of approximations. I think at least I have a general position here that I'm sympathetic to taking approximations seriously, which is when sometimes approximations, the fact that they can be, for instance, in planetary dynamics and space science, the Patch-Konik approximation. Patch-Konik approximation works in certain circumstances because of the way all the forces are acting. So it's we should learn something about those situations, and just carrying that over. So that's a Patch-Konik approximation, is where you can use an approximate force function. When a satellite, for instance, is in the gravitational basin of a particular planet. You can ignore all the other forces. You really can, because putting those forces doesn't actually very much change the trajectory that the thing follows. So approximately, it just is that. And of course, because in science everything's approximate, we should learn something from the fact that you have managed to identify the major determinants of the behavior, the kind of the shape of the problem. So I think that's. I think we ought to learn from approximations. There's a whole section in this paper that, that my bit was kind of about that, and we shouldn't throw away. We shouldn't absolutely look at what's fundamental, and we should be looking at the approximations. And I think this is very often the case where we're looking in exactly the wrong place if we spend too long thinking about this in terms of the quantum mechanical measurement problem, because then we're attending to an awful lot of structure which has played no part in the explanation. So whether the world splits into two, or whether none of that makes any difference down here. Gerardi, Rimini, and Weber probably isn't going to make a big difference to what's going on hereafter. We've got perfectly good explanations. We just have to attend to the right part of them to learn exactly how quantum mechanical structure arises from quantum mechanics.
Great. Okay. Anybody else? Let's have a final question, maybe, if any. Yeah, Alex.
Thanks. Yeah, I just quickly. two very short things. So first is, I think that what you just said was really interesting, but the conclusion that the Girardi, Rimini, Weber wouldn't make much difference. I guess that like there's a sense in which I think that some of these questions are like metaphysical questions, and the different interpretations of quantum mechanics do lead to very, very big differences in the way the world is. And if strong emergence is true, then that again would be a very different way in which the world is. And so insofar as we're interested in those, then I do think that even the very, very small differences that such interpretations might make are ones to which we should attend. And if one of these interpretations would obviate the case for strong emergence, then that would be very interesting. But the second thing was that I totally accept your point that in a sense we beg the question against strong emergence, because I think that what you demonstrated in your talk in a very, very clear way was that what we should take in some sense to be required for a resolution of the measurement problem goes far beyond what has so far been given. And so like there are two different ways to go with this. One could then say like, okay, well, these are different problems, the measurement problem is a different problem of molecular structure. Or you could say like, neither is resolved, but both resolve in the measurement problem, i.e. both understanding, for example, how you can end up with a live cat and a dead cat and a superposition, and how that kind of incredibly complex structure emerges, and the problem of the molecular structure require much more than have been given so far. So one might think that the original, and so I guess the question is like, are you all right with thinking about these kind of resolution of the measurement problem as kind of a programmatic attempts that, if they were fleshed out with the right kind of detail about how stability comes about and how systems end up being effectively non-interacting in real sort of physical, chemical ways, that might allow us to resolve both sets of problems? That both could be resolved in the same kind of way, but both require far more detail than has yet been given.
Yeah, absolutely. Yeah, and the only thing I would say is that it might be that there's different things going on, so different ways of different mechanisms of decoherence might be applying. They might be coming from different. I mean, so it might be this one of those cases where it's not just under determination, because it's there's different things going on in different cases. I don't know. It seems to be. That's why I thought that that the symmetry explanation, this came up with Olympia's talk as well. I mean, I just think the symmetry breaking thing is just a different discussion and a different kind of way of thinking about how this could arise than the measurement problem one. Although they can have, you can give them the form, they can look mathematically the same. They just look, that is if you're really pedantic, as I was, about how you formulate the measurement problem and these things that this discussion of Anderson's. So I don't know. So
just on that, I'd suggest David Wallace's paper on spontaneous symmetry breaking.
Yes, I've had that on my to-do read list.
That really changed the way I think about symmetry breaking, but I mean, it is of course from a very particular perspective.
I mean, my expectation of all these things is just like I think about emergence, is that we've people who think about things in quite abstract terms so often. Sometimes we're thinking about them in too abstract terms to really get what's going on, and then that even the things that are going to be a solution are going to be actually look quite different in the way they play out in different cases. So I wouldn't be, I mean, symmetry breaking, I don't know, I can never understand. I don't get the rules of what counts as symmetry breaking and what doesn't. I mean, I've had condensed matter physicists tell me that there's no symmetry broken in the case of enantiomers, because look, you've got this simple case, anyway.
Okay, well, we are running well over time. Thank you all very much. I would just like to say that Alex, I support Alex's last point that if they've done nothing else, then maybe they've highlighted the analogy between a Schrodinger's cat situation and the isomers situation. And that to me seems like too much of a coincidence not to be correct, if you like. In other words, if you solve one, you solve the other, which I think, Robin, you've agreed to. So
I don't.
all right. That's just my.
Maybe to different degrees. That's the thing.
Right.